Okay, so please excuse me if I express myself in English. So I'm going to focus on the first mission that Patrick mentioned, which is the scientific mission of CERN. And there's various different aspects of fundamental physics that we're working on, obviously. And I'm going to focus, closely down onto one topic, which is the quest for the Higgs boson. Now this picture here, is there a light? Yes, light. Yeah. So this shows you, whoops. This picture here shows you the region of Geneva. On the right-hand side, you see the airport, which sets the scale for the Large Hadron Collider. That's the big accelerator where the Higgs boson has been found. Airport runway is about 5 or 6 kilometers long. The circuit here is about 27 kilometers. Actually, of course, from the plane, you don't see the accelerator because it's buried in a tunnel, on average about 100 meters underground. So this is obviously a very big scientific venture, and as Patrick has already mentioned to you, there are thousands of scientists from around the world who have been participating in it. And Mohammed is one of them, and he'll tell you a little bit more about the Moroccan participation in just a moment. So I said I was going to focus on the search for the Higgs boson. So this is a picture of Mr. Higgs. So he came up with his theory in 1964. This picture was actually taken in 1965 when he was working out some details of his theory. And if you look here very carefully on his desk, you may see some of his scientific secrets. Now, I wanted to put this quest for the Higgs boson in a somewhat broader context. And so here I've got the history of the universe so far. So we know that it started about 13.8 billion years ago with a Big Bang. Please don't ask me why the Big Bang. That's the theologian's problem, not mine. So what we physicists and astrophysicists try to do is to understand what's been going on since the Big Bang. So of course the astronomers with their telescopes, they can see galaxies, they can see stars, they can see a long way back towards the Big Bang, but they can't actually see the beginning. And that's because right at the beginning of the universe, it was extremely hot, extremely dense. It was a plasma, and light does not shine through it. The only way to find out what was happening in that very early period of the universe's history is to recreate the conditions of that early part of the Big Bang in the laboratory. And that's what particle physicists try to do with our experiments at accelerators. So we try to understand, on the one hand, what makes up the universe, and also, of course, how it evolves. So I include this picture just to remind people that we really are studying the ordinary matter that makes up the universe, not just some fancy stuff that only exists in laboratories. No, we're really interested in the constituents that make up you, me, the stars, and the galaxies. So, of course, everybody knows that we're made of atoms. Those atoms have electrons in the clouds around much smaller nuclei. In the first half of the 20th century, it was realized that those nuclei are made up out of protons and neutrons. And in the second half of the 20th century, it was realized that those protons and neutrons are made up out of smaller things we call quarks. And it's these quarks and the electrons and related particles that are somehow the boundary of our current knowledge. So what we have to do now is to understand better these fundamental constituents, and of course always also the forces between them. So we have what we call a standard model of the visible matter in the universe that was proposed in the late 1960s by Abdus Salam, whom you see here, originally from Pakistan, and by two American theorists, Glashow and Weinberg. So their theory made essential use of the ideas that were proposed by Peter Higgs and others in the earlier 1960s, ideas that I'll come back to in a moment. So experiments at CERN in the early 1970s found the first evidence in favor of this standard model, and experiments at CERN in the 1980s, 1990s, also elsewhere, confirmed many of the predictions of the standard model in great detail. So what does this standard model consist of? Somebody asked me in the coffee break whether we discovered any new particles recently, so I'll give you the list, okay? So ordinary nuclear matter, as I mentioned, is made up out of quarks, and we know that there are 6 of them. I mentioned the electron, which makes clouds around nuclei in atoms, and there's a couple of heavier electron-like particles that were discovered in cosmic rays and in accelerators. There are also neutrinos, very light, weakly interacting particles, which made a lot of news about a year and a half ago, unfortunately for all the wrong reasons. So then we distinguish 4 fundamental forces between these particles. So 2 of them are very familiar, gravity, electromagnetism, and then inside the nucleus there are 2 other forces. There's a strong force that holds it together, and the weak force that's responsible for forms of radioactivity. So I hope I've answered your question. So in some sense, what you see on the screen, I like to think of as the cosmic DNA. These particles, their properties, encode all the information that you need to make the visible stuff in the universe. Well, almost all the information. There was one important detail missing, which is that most of these particles have masses. The electron, for example, it's the mass of the electron that determines how large atoms are. If the electron had no mass, there wouldn't be any atoms at all, because atoms would run away from nuclei at the speed of light. There's a particle here that's responsible for the weak force of radioactivity. If this particle didn't have a mass, the weak force would not be weak, and we'd all glow in the dark. So it's clearly very important to understand where the mass of these elementary particles comes from. So just to put this question in a bit more context, so many of you will remember dimly from school that you learnt that weight is proportional to mass, right? That's what Newton told us. And everybody knows that energy is related to mass, E equals mc squared. Unfortunately, Newton and Einstein somehow forgot to explain where the mass comes from in the first place. And that's where Mr. Higgs comes in. And that's his theory on the blackboard behind him. And don't worry, there's no exam at the end of the talk. Now, it's an absolutely crucial aspect of his theory that there should be a particle. And let me try to explain what is the motivation for the existence of this particle. And to do this, I'll use an analogy. So, according to the theory of Mr. Higgs and his colleagues, the entire universe is filled with a medium, a universal, homogeneous, isotropic, featureless medium. So, as an analogy, I ask you to think of Siberia and a field of snow. So there's this snow as far as the eye can see and even further. Now what happens when you try to cross this snow? I hope our Moroccan friends will excuse this analogy, by the way. So if you're a skier, you skim very quickly across the top of this snow field. You don't sink into the snow. By analogy, you don't interact with the Higgs field. You go very fast. That's like a particle with no mass that travels at the speed of light. So, no interaction with the Higgs field, speed of light. Think skier. Then maybe you have snowshoes. Then you go a bit slower, you interact with that Higgs snow field. You go at less than the speed of light, you're a particle with mass, an electron, maybe. And then finally, maybe you try to walk across Siberia. If you do that, it'll take you a long time. You'll go very slowly because you're going to interact very deeply with that Higgs snow. That's like a particle with a big mass. So that's the basic idea. Universal medium, and if you interact with it, you have a mass. Now the question is, what is the smallest unit of snow? Or in particle language, what is the quantum of this Higgs snow field? So in the case of snow, we know the answer. It's a snowflake. And the quantum of the Higgs field, the smallest unit of the Higgs field, is what we call the Higgs boson. And that is, if you like, the flaky theory that experiments at CERN have set out to test. So this is an example of a computer simulation of what a Higgs boson might look like. So in this simulation, two protons collided along this axis. They produced dozens of particles. Their energy was converted into lots of other particles. Among them, the Higgs boson. But the Higgs boson you don't see directly because it's an unstable particle. It doesn't leave a track. Instead, in this simulation, it decayed into these two particles over here and these two particles over there. So what we have to do at the LHC is to produce billions and billions of collisions, and with very powerful computer systems, sift through these billions and billions of collisions to find the occasional Higgs boson. So this is a picture of what goes on inside the tunnel. I remind you, 27 kilometers in circumference, 100 meters underground, and these here are the magnets that direct the particles around in circles so that they can collide. So when it's in full operation, you've got thousands of billions of protons going in each direction. Each of them has approximately the energy of a fly. And they make perhaps a billion collisions per second. And with those collisions, we hope to understand what is the origin of mass, whether there's a Higgs boson or not. The nature of dark matter, I didn't talk about that, but astrophysicists tell us that most of the matter in the universe is actually invisible dark matter. What's the plasma that filled the very early universe, and so on. So as I said, there's quite a number of scientific objectives, but I'm just going to focus on one, namely the Higgs boson. So there are 4 big experiments looking at these collisions, and 2 of them, this one down here called CMS, this one up here called Atlas, they are looking and have discovered the Higgs boson. They're looking for other new particles. You asked me whether there are any more particles to come. Yes, we expect more particles, but so they're still looking. Right. And this is the experiment that has the participation of Morocco that Mohamed will talk about in just a moment. So the accelerator started producing high-energy collisions in 2010, and over the first year or so, it rediscovered all the previously known particles. And this, for example, is one of the heaviest previously known bosons. which decays into two energetic particles. Very beautiful event. Now, it was sometime around the middle of 2011 that maybe the first evidence for the Higgs boson started emerging. And of course, on July the 4th, 2012, when the discovery was announced, there was what might be described as mass Hysteria among particle physicists, at least. So let me show you a couple of the events that triggered this hysteria. So here again from our friends in Atlas. Here's an event where you've got 1, 2, 3, 4 energetic particles coming out. So remember that the heaviest previously known boson decayed into 2. This one decays into 4. It must be something heavier, something new. And this is an example from the competition, the CMS experiment. So this particular example of a decay into 2 energetic neutral particles which deposited lots of energy up there and down there. So it was the observation of events like these that led both CMS and Atlas on the 4th of July of last year to announce the discovery of a new particle. So I'm a little bit embarrassed because I don't think we have a Moroccan newspaper here. Even a French? Le Monde. Le Monde, quand même. But if you could send me a copy of a front page of a Moroccan newspaper, I mean, yeah. Okay. But I think that this actually makes the point that this is a global discovery with stakeholders all over the planet. It's not a bunch of Europeans working in Geneva. It's a global discovery that everybody, well, many countries participated in. And this is a picture of the seminar where the discovery was announced. So these are some of the previous CERN directors general, and this is the guy who actually built the accelerator, a guy called Lynn Evans. And this is a picture of Peter Higgs, and this is one of the other original proponents of this general idea of the snow field, Francois Anglaire. And although they proposed this idea in 1964, this was the first time they met, 48 years later. Fortunately, they seem to be on good terms. So I hope, yes, this is an animation that shows you how the Higgs signal grew during time in the Atlas experiment. And if you look with an optimistic eye, you can see this bump here, and that bump, that's something statistically significant. That is an element in the Higgs discovery. And this is the same thing for those decays into 4 charged particles that I mentioned. And over on the left, is this working? Yeah. This is the previously heaviest known boson. This is a background, and this is the Higgs sitting up here in the middle. So there's no doubt, there is a new particle there. So just to bring you up to date, this is a compilation of the data that was shown a couple of months ago. So here you just see data fluctuating statistically around 0. No Higgs boson on the left, no Higgs boson on the right, but here in the middle there is uncontestably something new, and we're now trying to understand whether indeed this is precisely the Higgs boson that was predicted by now 49 years ago. And I can't resist showing a summary of the data that I did with my student. The red line is the standard model prediction. The data you can see agree very, very well with the standard model prediction. So Peter Higgs is surely smiling. So the existence of the Higgs is a big deal. Without it, there would be no atoms. The weak interactions would not be weak. We'd all glow in the dark if we existed at all. So as I said, the existence of this particle is surely a big deal, although it leaves open questions and scope for yet more particles. So perhaps I'll finish with this, so I won't go through to the end of my slides. I think this is a good place to stop. I'd just like to share with you a meeting that I had with Mrs. Thatcher in 1982. Just in case you're confused, she's the one on the right. So, what do you do, young man? So I said, well, I think of things for the experiments to look for, but then of course I hope they find something different. So Mrs. Thatcher, of course, liked things to be the way she liked them to be. Wouldn't it be better, young man, if they found what you predicted? So I said, well, you know, then we wouldn't know how to progress and learn more. And so in the same spirit, I think we particle physicists hope and believe that maybe this is not exactly the Higgs boson predicted in the standard model, and maybe there are other particles waiting to be discovered. Thank you.